Hello students, it is lecture 4 of mathematical physics, numerical methods. Okay, so today we will solve some questions on interpolation using various techniques like Lagrangian method and Newton forward difference formula and backward difference formula, as well as go for another topic of mathematical physics numerical methods, that is differentiation or differential equation. We will look it forward. Okay, one thing is pretty sure, that root finding and integration is one of the most important topic with respect to any competitive exam or any high level exam. Like Newton-Raphson is one of the most common topic which generally appear in the question paper. Okay, so firstly we will solve this question of interpolation. In this question, a table data is given below, xi and fxi, 1, 2, 3, 4, 5, and the data is 5, 9, 12, 16 and 20. So firstly we will solve, and what do we need to calculate is calculate f2.5. like we need to find the function that is in between 2 and 3, that is 2.5, the function for 2.5. okay, there are like 2-3 methods that we are going to use. The first one will be using the Lagrangian method. So as we know the formula for Lagrangian method, we discussed in last video that for Lagrangian method, just a second, yeah, here is the formula. If 3 data points are given, the Lagrangian formula is px, the Lagrangian polynomial px formula for the polynomial is px is equal to f naught x minus x1 into x minus x2 upon x naught minus x1 x naught minus x2. Similarly, plus fx1 f1 into x minus x naught x minus x2 upon x1 minus x naught x1 minus x2. Can you see the repetition, like x minus x naught x minus x2? okay, x1 is missing here. And similarly on denominator, what we do is x1 minus x naught x1 minus x2 x1 minus x3, if there are like more terms than this. So whenever we will write this Lagrangian formula for this particular polynomial, the number of characters are 1, 2, 3, 4, 5. So the formula will be px is equal to f naught into x minus x1 x minus x2 x minus x3 x minus x4 upon x naught minus x1 x naught minus x2 x naught minus x3 and x naught minus x4. And similarly for plus f1 into x minus x naught x minus x2 x minus x3 x minus x4 divided by x1 minus x naught x1 minus x2 x1 minus x3 and x1 minus x4. And similarly it continues for all 5. okay, then on putting out the values of 2.5 at the place of x and using all the values of taking this one as x1, this one as x2, this one as x3, this one as x4 and this one as x5, and this as fx1, fx0, fx1, fx2, fx3 and fx4, we have this huge calculation. okay, and after this huge calculation the result we get is 10.4. okay, so this huge calculation is the reason, that's why we don't use Lagrange formula generally unless it is mentioned in the question. okay, we do not use Lagrange formula because it involves large amount of calculation, and we use it only in the scenario when it is specially mentioned in the question. As I have mentioned it here, as the calculation goes too complicated, we avoid using Lagrangian method. okay, now what we will do is solve the same question with Newton forward difference formula and Newton backward difference formula. okay, now what we do, we write the same table and we will solve that question with Newton forward difference formula. okay, we have written here xi, we have written here fi. Now del f, What was del f? Do you remember, like the last video where we were writing the formulas? Del f will be this value minus this value, 4. 12 minus 9, 3. 16 minus 12, 4. And 20 minus 16, that is 4. Now del square f will be this 3 minus 4, minus 1. 4 minus 3, 1. 4 minus 4, 0. Del cube f will be 1 minus minus 1, that is 2. And 0 minus 1, that is minus 1. And del raised to power 4f will be minus 1 minus 2, that is minus 3. Okay. What will be s? S will be x minus x naught upon h. Okay. What is the given x? 2.5. X naught is the first value. What is the first value of x? 1. 2.5 minus 1 upon 1. So what we get s as 1.5. Now we write Newton forward difference formula for the same question. Okay. What is Newton forward difference formula? Px is equal to f naught, that is the first term, plus s del f naught plus s into s minus 1 del square f naught upon 2 factorial plus s minus 1 s minus 2 upon 3 factorial del cube f and s minus 1 s minus 2 s minus 3 del s power 4 f naught upon 4 factorial. Okay, there are 5 terms, we have these 5. If there would have been more, we would have gone further. Okay, now we put the values of s, we put the values of del f naught, del square f naught. What is del f naught? This is del f naught, del square f naught, del cube f naught, del raised to power 4 f naught. Okay, we put these values and the answer we get here is 10.43. Okay, now when we were doing the same with Lagrangian method, what the answer was? 10.4. It means that answer is basically the same, like answer revolves around the same figure. But the thing is, the Newton forward difference formula gets easier when it comes to calculation as compared to the Lagrange formula. Now we do the same thing with the backward difference formula. For backward difference formula, what is s? S is x minus xn upon h. Xn is the final term, that was 5. To 2.5 minus 5 upon 1, which is equal to minus 2.5. Okay, now we write the formula for backward difference. Newton for backward difference formula, px is equal to fn, that is final term, plus s del fn upon 1 factorial plus ss plus 1. Earlier it used to be s minus 1 in forward difference formula, but in backward difference formula it is s into s plus 1 del square f upon 2 factorial and then s plus 1 s plus 2 upon 3 factorial del cube f naught fn and s plus 1 s plus 2 and s plus 3 upon 4 factorial del 4 fn. Okay, we put out the values and what answer we get here is 10.4297, which is close to 10.43. So one question, 3 methods, answer is literally the same, but with what we are choosing here is Newton forward difference or backward difference formula for better calculations. Okay, now the next topic that we are going to study is numerical method for solving differential equation. So there is a differential equation, dy over dx is equal to fx comma y. Okay, like it is some function which is dependent on x and y. Okay, with x is equal to x naught and y is equal to y naught, initial condition given. So numerical methods need an initial condition, like initial condition is must for numerical methods. Okay, for solving differential equation for numerical method. Now what we need to do, we need to find yx. Okay, now as we mentioned the function fx comma y, if we expand this function about x naught y naught with Taylor expansion, what we get here is fxy is equal to fx naught y naught plus x minus x naught del f by del x, x naught y naught plus the same thing for y goes, like y minus y naught del f upon del y at x naught y naught. Okay, so this first method that we are going to use here is going to be quite crude approximation. Okay, it means that in this method what we will do, we will ignore the later half. Okay, and what we take here is fxy is nearly equal to fx naught y naught. What we did here, we expanded the function and ignored rest of the term except the first one. Okay, and it is pretty crude approximation. It's never gonna give you the exact answer close, like it takes you a margin away from the answer. But yeah, it is one of the method, like a crude method with large amount of error too. Okay, so what we did here, like dy over dx is equal to fxy, so dy over dx is equal to fx naught y naught, which we just now let. Okay, taking ds that side, we integrate. So what we get, y1 minus y naught is equal to f x naught y naught h. Okay, how h? Because we integrated it for some interval h. This interval is quite small. Okay, because if the interval is larger, it's gonna get drastically wrong. Okay, to maintain the sanity of the equation, we keep that interval, we keep that h, we keep that range of integration pretty small. Okay, so it is from x naught to x naught plus h. Now since it is a, like, what do you call it, it's a constant value of x naught y naught, so what we get here is after integration y minus y1 minus y naught is equal to fx naught y naught into h. So what is y? Like y1 is equal to y naught plus h into fx naught y naught. It is the Euler's formula or Euler's formula, whatever we call it. Okay, this is the Euler's formula that we have, like y1 is equal to y naught plus h into fx naught y naught. Okay, now for this y1 we take x1, and x1 will be like x naught plus h. Okay, at x2, so as x1 is equal to x naught plus h, we take the next interval, that is x2 is equal to x naught plus 2h. What we are doing here is increasing the interval by h. Okay, and what will be the change in y? y2 is equal to y1, that is the initial one. So y2 is equal to y1 plus hf x1 y1. Okay, see, it's just the repetition, but what we are here doing here is changing the values. Okay, for example, at x3, what is x3? X naught plus 3h, or basically it is x2 plus h. Okay, and what is y3? y3 is y2 plus h fx2 y2. Okay, and if we similarly do it for n interval, like the nth interval, what we get here is xn is equal to x naught plus nh. Okay, now as we said here, like xn is equal to x naught plus nh, and yn is equal to yn minus 1. Okay, that is the last value, plus h, that is the interval, into f xn minus 1 yn minus 1, that is the value of the function at the values of x and y, the last values of x and y. Okay, and this particular formula is general Euler formula. Okay, this is the general Euler formula for differential equation. Now there is one more method which is like gives a better value as compared to this crude Euler formula, Euler method, and that is the Runge Kutta method. In Runge Kutta or Runge Kutta method, we were gonna write the formula and all. Later on we will discuss its theory, etc. So if at x1 is equal to x naught plus h, okay, so at x1 is equal to x naught plus h, y1 here is y naught plus m1 plus m2 by 2, okay. It is the formulation of Runge Kutta method, okay. And what is m1 here? M1 is h f x naught y naught, okay. And what is m2 here is h f x naught plus h comma y naught plus m1, okay. Now if we do the same thing for x2, what we do here is x2 is equal to x naught plus 2h or x1 plus h. What will be y2? Y2 will follow the same pattern. Y2 is equal to y1 plus m1 plus m2 upon 2. But the value of m1 and m2 changes here. The m1 will be h f x1 y1 and m2 will be h f x naught plus 2h or x1 plus h comma y1 plus m1, okay. This is the Runge Kutta method. Now we will understand it better when we will solve the question with it, okay. Now the problem given here is dy over dx is equal to x. I hope it is clear to you and visible to you well. At x naught is equal to 0 and y naught is equal to 0. Find y1 using step size 0.5, okay. First we will solve the question using Euler method or Euler method. H is equal to 0.5, x0 is equal to 0 and y0 is equal to 0. So what will be x1? X1 will be x naught plus h, okay, and x1 is equal to 0.5. Now what will be the y1? Y1 will be y naught plus h f x naught y naught. That was the formula. Like earlier we saw it, like here is the formula. Y1 is equal to y naught plus h f x naught y naught, okay. Y1 is equal to y naught plus h f x naught y naught. Y naught, the value of y naught given here is 0, okay. Now h is 0.5 and f x naught y naught. This function, if you put the values of x as x naught, which is 0, what will be the value of function? 0. Like dy over dx is equal to 0, or we can basically write fx comma y is equal to x, okay. So if we put the value of x naught y naught, what will be the value of the function? It will be 0. So y1 is equal to 0. Now when we do it for the second interval, like when we do it for y2, y2 is equal to y1 plus h f x1 y1, okay. Y1 is 0 as we have seen here, h is 0.5, okay. This time in the values of function we take x1 and y1, since the function has only x term, okay. If we take the values of x1, what is x1 this time? X1 is 0.5, so what we put here is 0.5 into 0.5, that is 0.25. So the value of y1 here attained is 0.25. When we solve it exactly, like do the exact calculation using analytical method, the answer we get for y is 0.5. Now you can see there is a huge difference, like it is 0.5 and it is 0.25. There is a marginal difference, marginally huge difference, I would say. So as we can see here, it is a huge difference between the exact answer and the attained answer, okay. Now we will solve the same question using second order Runge Kutta method, okay. Let's see how that is done. Now for this method, what is the formula? Y1 is equal to y naught plus m1 plus m2 by 2, okay. What is m1? H f x naught y naught. H is 0.5 x naught y naught when f x naught y naught is 0, okay. So m1 will be 0. Now if we find out m2, h f x naught plus h comma y naught plus m1. So whenever we go for putting the value into it, h is 0.5, that is the step size, that is the interval step size which is given to us, okay. Now the function here is fx1 y naught plus m1, okay. Now the function depends on x only. Whenever we put the value of x1, that is 0.5, we attain the value of function as 0.5. We did in the previous question just now we did it in the Euler method or Euler method. So 0.5 into 0.5, that is 0.25. So y1, the value of y1 is 0.25 divided by 2, that is 0.125. Now we go for y2. Okay, what is y2? Y2 is equal to y1 plus m1 plus m2 by 2, but m1 and m2 are different for this y2. Okay, now what is m1? M1 is h fx1 y1. We solved it just here, that is 0.5 into 0.5, that is 0.25, correct? And what is m2? M2 is h f x0 plus 2h, or basically x1 plus h comma y0 plus m1, y1 plus m1. Okay, but as you know, the function is dependent on x. Okay, what we have written here, x0 plus 2h, the h was 0.5, 2h will be 1. So the value of this function will be equal to 1. So that is m2 is equal to 0.5 into 1. Now when we put this value over here, y2 is equal to y1, that is 0.125 plus 0.25 plus 0.5 upon 2, that is 0.75 upon 2, which is equal to 0.125 plus 0.375, and after calculation we get it as 0.5. Now what do we see here? Runge Kutta method is more like a better method than going for the Euler method. It gets close to the answer, and in some of the scenarios the answer is exactly the same. Now here is one of the integration that we will be solving using the Simpson 1/3 rule. It is just for practice purpose. Okay, we have finished the important topics of numerical method. Rest you can practice a lot, and if there is any query, do comment down. And yeah, so what's given here in the question, we need to integrate it or calculate. Step size 0.25, integrate 1:2 e raised to power minus x dx using Simpson 1/3 rule. As we all know, first we will find n. N is final minus initial upon step size, that is 2 minus 1 divided by step size, that is 0.25. So n is equal to 4. Okay, it's divided into 4 blocks. 1, it's 2, this point, like first block, second block, third block, fourth block. Okay, this is f0. So it is f0, f1, f2, f3 and f4. Okay, what we heard about the Simpson 1/3 formula, I is equal to h by 3, the first function like f0, the last one, plus 4 into sum of odd ones, plus 2 into sum of even ones. The odd ones are f1 and f2, f3, and even one is f2. On putting out the values, we use calculator for these values, and the answer we get here 0.232. So it was one question of Simpson 1/3 rule. Kindly watch all 4 videos of numerical method. It is an important topic, and if you cover these videos, I hope your problem will be sorted out. Thank you.